Evolution is the major force that defines our bodily shape as well as our built-in instincts and reflexes. We also learn to change our behavior during our lifetime. This helps us cope with changes in the environment that cannot be predicted by evolution. Organisms that have a short life in a well-defined environment may have all their behavior built in, but instead of hardwiring into us all sorts of behavior for any circumstances that we could encounter in our life, evolution gave us a large brain and a mechanism to learn such that we could update ourselves with experience and adapt to different environments. When we learn the best strategy in a certain situation, that knowledge is stored in our brain, and when the situation arises again, when we cognize means to know the situation, we can recall the suitable strategy and act accordingly. Learning has its limit though. There might be things that we can never learn with the limited capacity of our brains, just like we can never learn to grow a third arm or an eye on the back of our head, even if either would be useful. See Leahy and Harris, 1997, for learning and cognition from the point of view of psychology. Note that unlike in psychology, cognitive science or neuroscience, our aim in machine learning is not to understand the processes underlying learning in humans and animals, but to build useful systems, as in any domain of engineering. Almost all of science is fitting models to data. Scientists design experiments and make observations and collect data. They then try to extract the knowledge by finding out simple models that explain the data they observed. This is called induction and is the process of extracting general rules from a set of particular cases. We are now at a point that such analysis of data can no longer be done by people, both because the amount of data is huge and because people who can do such analysis are rare and manual analysis is costly. There is thus a growing interest in computer models that can analyze data and extract that information automatically. From them, that is, learn. The methods we are going to discuss in the coming chapters have their origins in different scientific domains, sometimes the same algorithm was independently invented in more than one field, following a different historical path. In statistics, it's going from particular observations to general descriptions is called inferences, and learning is called estimation. Classification is called discriminant analysis in statistics. Before computers were cheap and abundant, statisticians could only work with small samples. Statisticians, being mathematicians, worked mostly with simple parametric models that could be analyzed mathematically. In engineering, classification is called pattern recognition, and the approach is non-parametric and much more empirical. Machine learning is related to artificial intelligence because an intelligent system should be able to adapt to changes in its environment. Application areas like vision, speech, and robotics are also tasks that are best learned from sample data. In electrical engineering, research in signal processing resulted in adaptive computer vision and speech programs. Among these, the development of hidden Markov models (HMM) for speech recognition is especially important. In the late 1980s, with advances in VLSI technology and the possibility of building parallel hardware containing thousands of processors, the field of artificial neural networks was reinvented as a possible theory to distributed computation over a large number of processing units. Over time, it has been realized in the neural network community that most neural network learning algorithms have their basis in statistics. For example, the multi-layer perceptron to is another class of a non-parametric estimator, and claims of brain-like computation have started to fade. In recent years, kernel-based algorithms such as support vector machines have become popular, which, through the use of kernel functions, can be adapted to various applications, especially in bioinformatics and language processing. It is a common knowledge nowadays that a good representation of data is critical for learning, and kernel functions turn out to be a very good way to introduce such expert knowledge. Recently, with the reduced cost of storage and connectivity, it has become possible to have very large datasets available over the internet, and this, coupled with a cheaper computation, have made it possible to run learning algorithms on a lot of data. In the past few decades, it was generally believed that for artificial intelligence to be possible, we needed a new paradigm, a new type of thinking, a new model of computation, or a whole new set of algorithms. Taking into account the recent successes in machine learning in various domains, it may be claimed that what we needed was not new algorithms but a lot of example data and sufficient computing power to run the algorithms on that much data. For example, the roots of support vector machines go to potential functions, linear classifiers, and neighbor-based methods proposed in the 1950s or the 1960s. It is just that we did not have fast computers or large storage then for these algorithms to show their full potential. It may be conjectured that tasks such as machine translation and even planning can be solved with such relatively simple learning algorithms but trained on large amounts of example data, or through long runs of trial and error. Intelligence seems not to originate from some outlandish formula, but rather from the patient, almost brute force use of a simple, straightforward algorithm. Data mining is the name coined in the business world for the application of machine learning algorithms to large amounts of data. This is from Wheaton and Frank 2005, Han and Camber 2006. In computer science, it used to be called knowledge discovery in database KDD. Research in these different communities, statistics, pattern recognition, neural networks, signal processing, control, artificial intelligence, and data mining followed different paths in the past with a different emphasis. In this book, the aim is to incorporate these emphases together to give a unified treatment of the problem and the proposed solutions to them.